Section 1 Introduction. Let's dive into the introduction. When we're dealing with a document that's too large for a language learning model, LLM, to handle in one go, we need to come up with strategies to extract the relevant information. The common approach is to break the document down into smaller, manageable text chunks that are similar to the user's query and might contain the answer. However, this method falls short when dealing with documents that have a complex structure, like web pages, PDFs, or presentations. For example, if a user asks, "Can you summarize the key takeaways from pages 5 to 7? Or, what year, in Table 3, has the maximum revenue?" The current methods would struggle because they don't take into account the structure of the document. To address this, we propose a new approach, which we call PDFTriage. This method allows models to retrieve information based on the structure or content of the document. PDFTriage provides models with metadata about the document structure and a set of functions that can retrieve different types of structure. For instance, we introduce a function called fetch_pages, which allows the model to retrieve a list of pages. We found that by providing the structure and the ability to issue queries over that structure, PDFTriage enhanced models can answer several types of questions that traditional LLMs couldn't handle. To test our approach, we created a dataset of about 900 questions written by humans over 90 documents. These questions fall into 10 different categories, including document structure questions, table reasoning questions, and trick questions. We'll be releasing this dataset, along with the code and prompts we used. The main contributions of this paper are: 1. We've identified a gap in the current LLM approaches when it comes to answering questions about structured documents. 2. We're releasing a dataset of tagged question types and model responses to encourage further research. 3. We're introducing PDFTriage, a new method of prompting the model that improves its ability to answer questions about structured documents. The rest of the paper is organized as follows. We'll discuss related works, outline the PDFTriage approach, explain how we constructed the evaluation dataset, detail the experiments we ran, list the key takeaways from those experiments, and finally, discuss the limitations of our current work and future directions. In the next section, we'll discuss related works. Tool-augmented LLMs have become increasingly popular as a way to enhance existing LLMs. For example, React uses the Wikipedia API to generate a sequence of API calls to solve a specific task. Self-ask prompt provides the follow-up question explicitly before answering it. Toolformer uses self-supervision to teach itself to use tools. Talm augments LMs with non-differentiable tools using only text. Recently, Taskmatrix and Gorilla have focused on improving the ability of LLMs to handle millions of tools from a variety of applications. There have also been many works focused on benchmarks for tool-augmented LLMs. These include API Bank, which evaluates LLM's ability to plan, retrieve, and correctly execute step-by-step API calls for various tasks, and Tool QA that focuses on question answering using external tools. Retrieval augmented language models aim to enhance the reasoning capabilities of LLMs using external knowledge sources for retrieving related documents. For example, Hyde generates a hypothetical document by instructing an LLM, then encodes the document into an embedding vector, which is used to retrieve real documents that are similar to the generated document. More recently, Inter has been proposed, which iteratively refines the inputs of search engines and LLMs for more accurate retrieval. For more details on augmented language models, see the recent survey. Section Summary. Current approaches to document question answering often treat documents as plain text, which can lead to difficulties in answering questions that reference the structure of the document. To address this, we propose PDFTriage, a method that allows models to retrieve context based on both structure and content. By augmenting prompts with document structure metadata and retrieval functions, PDFTriage enables models to answer a wider range of questions over structured documents. We evaluate our approach using a dataset of human-written questions and provide code and prompts for further research. Section 2.2 Question Answering. We're going to delve into the topic of question answering, QA, and how it relates to structured documents. A lot of the existing research in QA doesn't really connect the questions to structured documents, but rather focuses on extracting answers from tasks like glue. For instance, QA datasets such as squad and natural questions are based on text-only documents, which lack tables or figures. Let's talk about document question answering. There are several datasets that have been created to measure different aspects of this type of QA. One of these is DOCV-QA, a visual QA dataset that uses scanned documents. Another recent study introduced a dataset called DUDE, which is used for understanding and evaluating documents. DUDE uses both scanned and digitally created PDFs. Both DUDE and DOCV-QA have questions that can be answered in a short form. On average, DUDE answers are about 3.35 tokens long, and DOCV-QA answers are about 2.11 tokens long. QASPER is another dataset that focuses on questions seeking information and their answers from research papers. These documents are parsed from raw LaTeX sources, and the questions mainly focus on the content of the document. The PDFTriage evaluation dataset aims to broaden the types of questions in these datasets, including questions that refer to the structure or content of the document, can be extractive or abstractive, and may require long-form answers or rewrites. Now, let's discuss PDFTriage, structured retrieval from document metadata. The PDFTriage method involves 3 steps to answer a user's question. First, it generates document metadata by extracting the structural elements of a document and converting them into readable metadata. Second, it uses an LLM-based triage to select the precise content from the document. Finally, it generates an answer based on the question and the retrieved content. We use born digital PDF documents as the structured documents that users will interact with. Using the Adobe Extract API, we convert the PDFs into an HTML-like tree, which allows us to extract sections, titles, page information, tables, and figures. This API generates a hierarchical tree of elements in the PDF, including section titles, tables, figures, paragraphs, and more. Each element contains metadata, such as its page and location. We can parse this tree to identify sections, levels, and headings, gather all the text on a certain page, or get the text around figures and tables. We convert this structured information into a JSON type, which we use as the initial prompt for the LLM. The content is then converted to Markdown. PDFTriage uses 5 different functions: fetch_pages, fetch_sections, fetch_table, fetch_figure, and retrieve. Each function allows the PDFTriage system to gather precise information related to the given PDF document, focusing on structured textual data in headers, subheaders, figures, tables, and section paragraphs. These functions are used in separate queries by the PDFTriage system for each question, synthesizing multiple pieces of information to arrive at the final answer. To start PDFTriage for question answering, we use the system prompt format of GPT 3.5 to input the following. You are an expert document question answering system. You answer questions by finding relevant content in the document and answering questions based on that content. Document. Less than textual metadata of document greater than. Using user prompting, we then input the query with no additional formatting. Next, the PDFTriage system uses the functions established in section to query the document for any necessary information to answer the question. In each turn, PDFTriage uses a singular function to gather the needed information before processing the retrieved context. In the final turn, the model outputs an answer to the question. For all of our experiments, we use the GPT-35 Turbo 0613 model. To test the effectiveness of PDFTriage, we created a set of document-focused question-answering tasks. Each task aims to evaluate different aspects of document question answering, analyzing reasoning across text, tables, and figures within a document. We also wanted to create questions that range from single-step answering on an individual document page to multi-step reasoning across the whole document. We collected questions using Mechanical Turk. Our goal was to collect real-world document-oriented questions for various professional settings. We sampled 1,000 documents from the Common Crawl to get visually rich, professional documents from various domains, then subsampled 100 documents based on their reading level. By collecting a broad set of document-oriented questions, we built a robust set of tasks across industries for testing the PDFTriage technique. In order to collect a diverse set of questions, we generated our taxonomy of question types and then proceeded to collect a stratified sample across the types in the taxonomy. Each category highlights a different approach to document-oriented QA, covering multi-step reasoning that is not found in many other QA datasets. We asked annotators to read a document before writing a question. They were then tasked with writing a relevant question in the specified category. Our taxonomy includes 10 different categories: figure questions, text questions, table reasoning, structure questions, summarization, extraction, rewrite, outside questions, cross-page tasks, and classification. In total, our dataset consists of 908 questions across 82 documents. On average, a document contains 4,257 tokens of text, connected to headers, subheaders, section paragraphs, captions, and more. We provide detailed descriptions and examples of each of the classes in the appendix. Section Summary. Existing work in question answering, QA, often focuses on extractive tasks and lacks grounding in structured documents. However, datasets like DOCV-QA, DUDE, QASPER, and PDFTriage aim to address this by incorporating document scans, born digital PDFs, and questions that reference document structure or content. PDFTriage utilizes document metadata and LLM-based triage to answer user questions, while the dataset construction involves collecting real-world document-oriented questions across various industries and question types. Section 5: Experiments. In this section, we'll discuss the experiments we conducted, the models and strategies we used, and the baselines we compared our results to. We'll also be releasing the code and datasets we used, so you can replicate our results. Our main experiment involved using our PDF triage approach to answer various questions from a selected dataset of PDF documents. This approach takes advantage of the structure of PDFs and the interactive capabilities of GPT 3.5 to extract answers more accurately and precisely than previous methods. We used two baselines for comparison. The first involved indexing the pages of each document using text embedding ADA002 embeddings. We then used cosine similarity to find the pages most similar to the query embedding. Each page's text was then used as context for answering the question until we reached the context window limit for a model. The second baseline involved concatenating all the document's text and then dividing it into 100-word chunks. Each chunk was then indexed using text embedding ADA002 embeddings. We then used cosine similarity to find the chunks most similar to the query embedding. Each chunk's text was then used as context for answering the question until we reached the context window limit for a model. For both baselines, we used a prompt to get an answer from GPT 3.5. The prompt was, "You are an expert document question answering system. You answer questions by finding relevant content in the document and answering questions based on that content." To measure the difference between PDFTriage and the retrieval baselines, we conducted a human labeling study on Upwork. We hired 12 experienced English-speaking annotators to judge the answers generated by each system. We asked them to evaluate several key attributes of each question document pair and the associated general questions. Our results showed that the largest group of questions, 43.3%, were categorized as easy, while roughly a third of questions were categorized as hard for various reasons. We also asked annotators to categorize questions by type using the same categories as section. Our annotation framework resulted in a dataset that's diverse across both question types and question difficulties. In our annotation study, we found that annotators favored the PDF triage answer over half of the time, 50.7%, and favored the chunk retrieval approach over the page retrieval approach. PDF triage performed substantially better than current alternatives, ranking higher than the alternate approaches across all the question types. We also asked the annotators to score PDF triage, page retrieval, and chunk retrieval answers across 5 major qualities: accuracy, informativeness, readability, understandability, and clarity. PDF triage answers scored higher than page retrieval and chunk retrieval across all answer qualities except for clarity. PDF triage had the highest scores for overall quality and answer accuracy. For the PDF document sample used in our study, the average token length of retrieved PDF triage text is 1568 tokens, using the GPT 3.5 tokenizer. The average metadata length of textual inputs in document JSONs is 4,257 tokens, using the GPT 3.5 tokenizer. While PDFTriage utilizes more tokens than page retrieval, 3,611 tokens on average, and chunk retrieval, 3,934 tokens on average, the tokens are retrieved from multiple sections of the document that are non-consecutive. PDFTriage helps overcome this issue through the multi-stage querying of the document, retrieving and adding context as needed for different document QA tasks. Section Summary. The authors conducted experiments to evaluate their PDFTriage approach for document question answering. They compared it with two baselines, page retrieval and chunk retrieval. Human evaluation results showed that PDFTriage outperformed the retrieval-based approaches in terms of answer quality, accuracy, readability, and informativeness. PDFTriage also required fewer retrieved tokens compared to the baselines and demonstrated strength in multi-step reasoning tasks. Section 6.4 PDFTriage performs consistently across document lengths. Our tool, PDFTriage, shows consistent performance regardless of the length of the document. We were curious to see if there was any relationship between the effectiveness of PDFTriage and the overall length of the document. To measure this, we compared the scores given by human evaluators for overall quality of PDFTriage's answers with the length of the document. We used a statistical measure called Pearson's correlation coefficient and found it to be -0.015. This value is very close to zero, suggesting that the length of the document doesn't really affect how well PDFTriage works. This is a positive finding as it means our technique can be applied to both short and long documents without any significant impact on its performance. The type of document, regardless of its length, doesn't seem to affect the overall performance of PDFTriage. One of the key features of PDFTriage is its ability to search for specific sections within the document. This eliminates the need to process documents with a lot of unnecessary information. PDFTriage can link different parts of a document together, which is particularly useful for tasks that span multiple pages, such as interpreting tables, tasks that require cross-referencing pages, understanding figures, and answering questions about the structure of the document. By focusing on the relevant context and ignoring irrelevant information, PDFTriage makes it easier for language learning models like GPT-3 to handle the reduced context size. This not only improves their performance but also reduces the computational and financial resources needed for document question answering tasks.